The ongoing activities observed in relation to the second prototype of the large, tailless combat aircraft known as the J-36 represent a clearly defined and advanced stage in its systematic development cycle. The recurrence of flight operations is not merely a repetition but a critical element of a structured test program. Each flight of the J-36 is a data-gathering mission designed to methodically expand the aircraft's certified performance envelope, which includes parameters such as true airspeed, indicated airspeed, altitude, angle of attack, and load factor. This incremental process ensures that the J-36 airframe's structural integrity and its flight control laws are validated across the entire spectrum of intended operational conditions. Stability and control engineers analyze data from these flights to refine the J-36's flight control system, which is of particular importance for its tailless design that lacks conventional horizontal stabilizers and must rely entirely on alternative control surfaces and its thrust vectoring nozzles for pitch authority. A specific and significant test event conducted during one of these J-36 flights was the functional verification of the aircraft's fuel jettison system. This system is a fundamental safety-critical component on most large aircraft, especially those like the J-36, which is designed for long-range missions with a high fuel fraction, meaning a significant portion of its takeoff weight is fuel. The underlying engineering principle addresses the disparity between the J-36's maximum takeoff weight and its maximum allowable landing weight. The stresses on the J-36's airframe and landing gear during a controlled takeoff roll are substantially lower than the concentrated impact forces experienced during touchdown. Therefore, if an emergency situation, such as a system failure, landing gear malfunction, or immediate tactical diversion, requires a return to land shortly after a heavy-weight takeoff, the J-36 would exceed its designed structural limits for landing. The fuel jettison system is the engineered solution, allowing the flight crew to rapidly reduce the J-36's mass to a predetermined safe landing weight. The execution of this test on the J-36 is a complex, data-driven procedure far beyond a simple visual demonstration. The test objectives are multifaceted and involve the collection of precise empirical data. Engineers verify that the actual fuel flow rate through the J-36's jettison nozzles matches the design specifications, ensuring the aircraft can lose weight at a rate sufficient for emergency scenarios. A critical analysis involves the fluid dynamics and trajectory of the jettisoned fuel. The design of the nozzle outlets and their placement on the J-36's airframe must ensure that the resulting fuel cloud, which typically atomizes into a fine mist, is directed completely clear of the aircraft's structure. This is vital to prevent any possibility of fuel ingestion by the J-36's engines, which could cause flameout or compressor damage, or contact with the airframe and stabilizers, which could degrade specialized coatings, damage composite materials, or create a fire hazard. Concurrently, the J-36's flight control computers and test pilots monitor the handling qualities throughout the jettison process. As fuel is dumped from various tanks, the J-36's center of gravity shifts. The test validates that the flight control system can automatically compensate for this shift or provides the pilot with adequate control inputs to maintain stable and predictable flight characteristics during the entire weight reduction sequence. The progression to this level of system testing on the second J-36 prototype is a strong indicator of the program's maturity and its iterative development. Philosophy. The first J-36 prototype's flights were likely dedicated to establishing basic airworthiness and fundamental flight characteristics. The fact that a second J-36 prototype, which has been observed to incorporate significant design revisions such as altered two-dimensional thrust vectoring engine nozzles and diverterless supersonic inlets, is now being used for subsystem validation indicates that the program has successfully passed its initial proof-of-concept phase. The commencement of tests on complex, non-flight critical but safety essential systems like fuel jettison signifies a transition into a more integrated testing phase for the J-36. This phase focuses on verifying the functionality and reliability of the aircraft's internal systems, moving beyond the basic aerodynamics and into the intricate network that makes the J-36 a complete and operational platform. This logical, sequential progression from airframe testing to system validation is a standard but conclusive marker of an advanced and accelerating developmental program for this new generation of military aircraft.